Today we are going to study about the second in our transition series, that is actinides. Actinide consists of 14 elements starting from atomic number 90 to 103. And the name of the elements is thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, novelium, lawrencium. All of these actinoids are radioactive elements. Only few of these exist in nature, like thorium, protactinium, and uranium. These are found in the natural ores, and remainings are all synthetic elements. These are formed by some nuclear reactions. And all of the remaining elements, or you can say all the transuranium elements which follow uranium, are highly radioactive. They have very small half-life period. So first let's see the electronic configuration of these elements. If you see the typical definition of actinoids, it says that the elements which have its last electron entering into the anti-penultimate f orbital. But if you see the thorium doesn't have any electron in the f orbital, but it is considered as an actinoid. So the configuration of thorium is radon. Radon is a novel gas that, so the electronic configuration of radon, and after that 5f0, because there is no electron in the f orbital, then 6d2, 7s2. This is the electronic configuration of thorium. After that, protactinium. So protactinium will have 2 electrons in its f orbital, that is 5f2, 6d1, 7s2. Thorium is the only F block element, only actinoid which will have 2 electrons in its d orbital. Otherwise you will see it has only all the other actinoids either have 1 electron or 0 electron in its d orbital. And even if you see the lanthanoids, they also have only 0 or 1 electron in its d orbital. So thorium is kind of have exceptional electronic configuration with 2 electron in its d orbital and 0 electrons in its f orbital. Now let's move to the third, that is uranium. Uranium have 5f3, 6d1, 7s2. And as you move down the group, the electronic configuration for neptunium is 5f4, 6d1, 7s2. Now on reaching plutonium, instead of having 5f5, 6d1, it has 5f6, 6d0, 7s2 electronic configuration. Americium again have 5f7, 6d0, 7s2. Now americium have 7 f electrons and 0 d electrons because of the extra stability provided by the completely filled f orbitals. Curium again have 5f7, 6d1, 7s2 electrons. Berkelium has 5f8, 6d1, 7s2. And stanium have 5, sorry, californium have 5f10, 6d0, 7s2. And stanium have 5f11, 6d0, 7s2. Fermium have 5f12, 6d0, 7s2. Mendelevium have 5f13, 6d0, 7s2. Novelium have 5f14, 6d0, 7s2. And Laurentium have 5f14, 6d1, 7s2. Now many of you might have a doubt regarding the electronic configuration, like this plutonium have 5f6 and no electrons in the d orbital. It could have had 5f5, 6d1, 7s2 electronic configuration, because there is neither some extra stability it is attaining, neither it has a completely filled orbital f orbital, neither it has half filled orbital. Then why that instead of having one electron in the d orbital, it has all the electron in the f orbital? So this could be a doubt. So what happened when you see the splitting of f orbitals, like we did in the d block elements? The d orbitals were splitting into T2g and Eg. Similar way, f orbitals also get splitted, and the arrangement in the splitted orbitals give extra stability to some of the electronic configurations. But we will not go into that much detail for f block elements. The simpler way to understand this is these electronic configurations are predicted based on the properties shown by the elements. So when scientists kept the option of these two type of electronic configuration for your plutonium, that is either 5f6, 6d0, 7s2, or 5f5, 6d1, 7s2, and they predicted the properties based on these two different electronic configuration. What they found, that the actual properties shown by the plutonium element are similar to that of the uh, that configuration which have 5f6 and 6d0 electrons in its electronic configuration. So they concluded that this should be the electronic configuration for plutonium. Similar way, the rest of the elements in the periodic table got their electronic configuration. Now moving on to the properties. We have already discussed that all the actinoids are radioactive, and elements other than thorium, proactinium, uranium, all the other elements in the actinoid series are synthetic or man-made. Now, physiochemical properties of actinoids. The oxidation state, there is a correction here. In this sentence, these elements usually exhibit oxidation state of +2, but it should have been +3. So actinoids also show +3 oxidation state. All the actinoids show +3 oxidation state. Some few elements show +2 oxidation state as well. Novelium particularly exists in the +2 oxidation state, while the naturally occurring actinoids, or you can say the first 5 6 elements of the actinoid series have variable oxidation state, like they show multiple oxidation state. For example, thorium show +3 as well as +4 oxidation state. So in case of thorium, +3 is not the most stable oxidation state. Like we have seen in the lanthanoids, all the lanthanoids have +3 oxidation state, which is more stable. But that is not the case with actinoids. Thorium shows the most stable state for thorium is +4 oxidation state. If thorium is present in the +3 oxidation state, it will get oxidized, and it will form +4 oxidation state. So the most stable oxidation state for thorium is +4. If you consider the oxidation state of protactinium, it shows +3, +4 as well as +5 oxidation state, but the most stable is +5. If you goes to the uranium shows 4 different oxidation state: +3, +4, +5 and +6, and +6 is the most stable in case of uranium. Now as you move to the neptunium, other than the 4 oxidation states shown by uranium, it also shows +7 oxidation state. So it shows the oxidation state +3, +4, +5, +6 and +7, but the most stable oxidation state here is +5. As you move again to plutonium also shows oxidation state varying from +3 to +7, but the most stable state in this case is +4. Now after this, all the elements other than novelium will have +3 as their most stable oxidation state. If you compare actinoids and lanthanoids majorly show +3 oxidation state, but actinoid shows +3 as well as some other oxidation states, and +3 is not the most stable oxidation state for all the actinoids. Few actinoids have the +3 as most stable state, others have other different oxidation states. Now if you discuss the physical state, all the actinoids are silvery white like lanthanoids, and these get tarnished when exposed to alkalis. If you consider the density, so they are very very heavy metals. All the elements other than thorium and americium are having very high density. Okay, if you consider the color, obviously color is shown due to the F transition, and actinoids have lot of incompletely filled F orbitals. So if you in general say that then actinoids form colored compounds, and the color depends upon the number of F electrons present in the orbital. But the elements which have incompletely filled F orbital will not, empty or completely filled F orbital, those will not show the color. Ionization energies, since these elements have very dispersed electron cloud, so they have very low ionization values, and also these are very electropositive because they exist in the bottom of the periodic table, and as you move down the group, the electropositivity of the elements increases. So they are very highly electropositive and hence very strong reducing agents. And actinoids have strong tendency to form complexes. Like lanthanoids, actinoids also show contraction in the radii. So again it has the similar explanation like the lanthanoid contraction. So these elements also show actinoid contraction, and hence the decrease in size is regular but very gradual. And actinoids are, since they are radioactive elements, most of them are used in the nuclear reactors, um, as a as for producing fuels, or they are also used in the atom bombs. um, Mostly they are used in the nuclear reactors for the fuel, and also in some cancer treatments, and in gas metals as a mixture of thorium and cerium nitrate. So gas metals are the chambers. These chambers have very high these chambers require very high heat energy. So the heat energy is produced by using a mixture of thorium and cerium nitrate in a ratio of 99 to 1. So this is all for the actinoids that we have to study. And there is one more thing, that is magnetic property. So again, since actinoids have unpaired electrons in its f orbital, so these show magnetic properties similar as in case of the lanthanoids. But since all of these are radioactive, so the magnetic properties of actinoids are not that predictable as it is in case of the lanthanoids. And in case of radioactive elements, there is always a uncertainty regarding the electronic configuration or some physical properties. So that way the actinoids are not that much clear in its properties. So that's it for the actinoids. If you have any doubts, please feel free to message in the WhatsApp group, or you can ask your doubts in the next class. Thank you.